With the Lewis structures of ionic compounds, we saw a transfer of electrons from one element to the other. With Lewis structures of molecules, we will see a sharing of electrons between the two atoms in the bond. One shared pair of electrons makes a single covalent bond. For example, each chlorine atom has a dot that is by itself. Those single dots can come together in the middle and be shared between both chlorine atoms. That pair of dots is a single bond. Instead of drawing a pair of dots for the bond, we could draw a line. One line in our structures is going to mean the same thing as two dots. It just looks a little cleaner and makes bonds easier to spot, so we usually draw them with the lines instead of the dots. Remember, in the Lewis dot symbol of individual atoms, we put the electrons in unpaired first and only pair them when necessary. In the Lewis structures of molecules, however, we want to put them in pairs whenever possible. There are two types of pairs, bonding pairs or lone pairs. Bonding pairs are pairs of electrons that create the bond. They are shared between the atoms. Lone pairs are pairs of electrons that belong to one atom only. How many lone pairs of electrons are on the oxygen atom in the Lewis structure for water? For now, I am giving you the Lewis structures, but very soon, you should be able to draw your own Lewis structures to answer this type of question. Is the answer A, 0, B, 1, C, 2, or D, 4? The correct answer is C, 2. The oxygen has two lone pairs. There is also a bonding pair between oxygen and each hydrogen. As we draw Lewis structures of molecules, we will be using a rule called the Octet Rule. The Octet Rule tells us that each element except for hydrogen should ideally have 8 dots around it, or the equivalent with dashes, since each element wants to have a full outer shell of electrons. Remember, the first shell only has a 1s orbital in it, so the maximum it can hold is 2 electrons. That is why hydrogen only wants a total of 2. All other elements have s and p orbitals in their outer shell, so they need 8 to fill up the s's and the p's. Take a look at the structures on this slide. They all obey the octet rule. The chlorine has 8 dots around it, or the equivalent, 6 dots and 1 dash, which represents 2 electrons. Each carbon has 8 dots around it, or the equivalent, 4 dashes. Each silicon has 8 dots around it, or the equivalent, 4 dashes. Each hydrogen has 2 dots around it, or the equivalent, 1 dash. You will never see hydrogen with a double or triple bond because it can only have 2 electrons next to it. You will also never see hydrogen as the central atom because it would need to make more than one bond, which would mean having more than 2 dots around it. You will only see hydrogen connected to one single bond. Anything else means the structure is wrong. A good rule of thumb to know is that for the nonmetals, the number of bonds is often going to be 8 minus the group number. For example, nitrogen is in group 5A, so it has 5 valence electrons. We expect it to have 8 minus 5, which is 3 bonds. We can see that in the ammonia molecule, for example. Oxygen is in group 6A, so it has 6 valence electrons. We expect it to have 8 minus 6, which is 2 bonds. We see that in the water molecule, for example. Fluorine is in group 7A, so it has 7 valence electrons. We expect it to have 8 minus 7, which is 1 bond. We see that in the hydrogen fluoride molecule, for example. This rule of thumb does not always work, but is a good way of checking to see if you are on the right track. We've seen that single bonds have one shared pair of electrons, or in other words, 2 electrons in the bond. Double bonds have 2 shared pairs of electrons, in other words, 4 electrons in the bond. For example, carbon dioxide has a double bond between carbon and each oxygen. Notice that each atom obeys the octet rule. For the octet rule, all of the electrons in the bond count for both atoms that they are between. Here they are doing double duty, completing the octets for both carbon and oxygen. Each oxygen has 4 electrons in lone pairs and 4 electrons in the double bond for a total of 8. Carbon has 4 electrons in each double bond for a total of 8 for carbon. Instead of drawing it with 4 dots between the atoms, we can draw 2 lines. Remember, each line represents 2 dots. The 2 lines go on top of each other like an equal sign. Triple bonds are made from 3 shared pairs of electrons. In other words, 6 electrons in the bond. We can see a triple bond in the nitrogen molecule. Again, for the octet rule, the electrons in the bond count toward both atoms. Each nitrogen gets 6 electrons from the triple bond and 2 electrons from a lone pair to make 8 on each nitrogen. Instead of drawing it as 6 dots, we can draw 3 lines on top of each other. The lengths and strengths of bonds depend on whether they are single, double, or triple bonds. I like to think of bonds like rubber bands. A single bond is like a single rubber band. It is going to be relatively easy to stretch, so it can be long, and it will also be relatively easy to break. Double bonds are like 2 rubber bands together. They will stretch less, so they will be shorter, and they will be harder to break. Triple bonds are like 3 rubber bands working together. They will be the shortest and strongest of all the types of bonds. For example, if we compare carbon-carbon bonds, the triple bond is the shortest at 120 picometers, the double bond is longer at 134 picometers, and the single bond is the longest at 154 picometers. The single bond is the weakest and easiest to break. It only requires 348 kilojoules per mole to break the single carbon-carbon bond. The double bond requires 614 kilojoules per mole, and the triple bond requires 839 kilojoules per mole. Select the longest bond in the following group. Is it A, carbon-nitrogen single bond, B, carbon-nitrogen double bond, or C, carbon-nitrogen triple bond? The correct answer is A, carbon-nitrogen single bond. It is like having only one rubber band. It is easy to stretch and will therefore be the longest. Sometimes when we make Lewis structures of molecules, it's as simple as pushing the Lewis dot symbols of the atoms together. We could scoot the hydrogen so that its electron fills the vacant hole in the bromine. We could scoot 2 hydrogens so that their electrons fill the vacant holes in the sulfur. The nitrogen is a little trickier. We would have to move some of the electrons around to make the triple bond in the middle. Perhaps you were taught this scooting method of making Lewis structures in high school. Although it works sometimes, it doesn't always work. I'm going to show you a 5-step method that you should always follow because it always works. After you finish drawing each Lewis structure, you should check for 2 things to be true. The total number of electrons in the structure needs to be equal to the number of valence electrons of all of the atoms in the molecule. If we are drawing the Lewis structure of a polyatomic ion, the charge on that ion will affect the number of valence electrons available. We will add electrons in anions and subtract electrons in cations. The other thing that we need to double check with each structure is that all atoms obey the octet rule. Remember, hydrogen only needs 2 electrons around it instead of 8. Also, we will talk about some exceptions to the octet rule, including when the central atom has more than 8 electrons around it. This will only be able to happen when the central atom is in period 3 or below, and therefore has access to d orbitals.